All right. Let's have a look at the following wheel mounted on a shaft, a fixed shaft of radius r, and somehow we are gonna find out what the moment of inertia J is. And we are doing that by pulling on the axis with the massless tape, and pulling that with a constant force F, so that the axis and the wheel slowly starting to spin, and then spin faster and faster. And when we have spun up a length L, so we start at 0, and then the tape is wind up to a length L, capital L. The system is rotating with the angular speed omega naught. And find the moment of inertia. Notation I naught here is not really relevant, since the moment of inertia is a constant. So it's not the moment of inertia for that moment when we have omega naught here, or after a time t naught. So let's just call it capital J. It's a constant of the system. So what do we know? Yeah, RF given in the problem. So the torque equation might be interesting here. The torque equal RF, since it's 90 degrees between R and F. So it's just simple RF. So we don't need to treat this as some kind of vector problem. And from the right-hand screw rule, we of course know that this torque, RF, is inside this so-called paper. And another relation we know is torque should be the moment of inertia times the angular acceleration, phi dot dot. And we know omega, yeah, that's just phi dot. And for circular motion, we know that the speed in this point here is given by the formula here. Omega times the radius r. But by definition, speed is also dx dt. So during the time dt, the length dx is unbounded here. So dx is a small length, depending on the velocity v and dt. So what we can do, we can multiply with dt here, and also here, and then we can integrate. So that's what you have here. Okay. And this integral we can do is just L. And this we cannot, because omega will depend on time, right? And we still don't know omega exactly. So we end up here, and we need to find out what might omega as a function of time be. And then we look at equation 1 and 2. And yeah, they should be equal, right? So the angular acceleration is r times f divided by j. So the angular acceleration is a constant. And the angular acceleration, it can be written like this, d omega dt, which is this constant here. And then we can integrate on both sides. So here, this integral will be omega. And since this is a constant, you can lift it out from the integral. And then the rest of it will just be t. So this is the omega as a function of t. And now we insert this result here in equation 3, which is that one. The problem was here we couldn't continue since we didn't know omega as a function of t. But now we do, right? So let's see what that will be. L equal r and an integral. Yeah. Omega t. But this is a constant. Lift it out from the integral. Here, this. And t remains inside the integral. And the antiderivative of t is, of course, t squared over 2. And then the limits. So you get t squared over 2 t naught here. So now you have L equal this part here. And so the moment of inertia, J equal this. And we can still simplify this a little bit. T naught squared. Actually, we have the function here. Omega equal this for any t. Also t naught. So if we say t naught here, then it's t naught here. At omega at the time t naught is just omega naught, right? So we get this. And then you can insert it here. So this here is that. Then insert t naught squared. It's this. You get this. And then you can simplify. You have this. Here's j squared. But it's a j here. So you can get rid of that and solve. So j equal this. And that's the final result. And from the problem text, if F is 10 Newton, L5, and omega naught this, you get moment of inertia should be 400 kilometers squared. And yeah, it's fine. And another thing which is important in physics is to always check that the dimension of your result checks out.